Here we're going to take a look at a buffer example problem to try to help with solving some of the stuff in the lab from the previous week. So we're going to consider this buffer. It's 250 milliliters. It's made from a solution which is 0.2 molar in formic acid and 0.15 molar in sodium formate. We want to know first what is the initial pH, which we'll solve first, and then second, if we stress this buffer by adding 4 milliliters of 0.1 molar NaOH, what will be the new pH? And the problem lets us know the Ka for formic acid is 1.80 times 10 to the negative fourth. This is something you can look up if, for example, you're working in something in the lab and you don't know the Ka. Just look it up in the back of your text. It's part of the index there in the appendices, and you can find it there. So, let's take a look at this. The first thing we need to identify is which of our compounds is an acid and which is their base in our buffer. So the best way to do this is by looking at the number of hydrogens available between the two compounds. Your acid is going to be your proton donor, whereas your base is going to be your proton acceptor. So in an acid conjugate base pair, or a base conjugate acid pair, what you're looking for is you're looking for one of them to have one more hydrogen. That's your acid. So in this case, we have formic acid has 2 hydrogens, whereas sodium formate only has 1 hydrogen. That's a good identifier that it's the formic acid that's an acid. Also, in retrospect, it has the name formic acid. That helps. But if you'd only seen HCOOH in your problem, you could still identify it as the acid without having been given the formal name. The other thing to notice is as a 1211 refresher that if you put NaHCOO in water, and you're going to notice this for a lot of our conjugate bases that we work with, this is going to be completely soluble and it's going to break apart into 2 parts. It's going to break apart into the ion Na plus and the ion HCOO minus. So this is actually the conjugate base, the HCOO minus part. The reason we have the sodium there at all is you won't just have a bottle that just says HCOO minus on it. It needs something else with it. It needs a counter ion to balance out that charge difference so that we can get it into solution. So while the sodium plus is there, it's not going to do anything in the buffer in terms of changing the pH at all. So if you haven't gotten there yet, we'll discuss why that is when you're discussing salts and how to figure out whether they're going to affect pH or not. It has to do with the fact that sodium is a conjugate acid for the base sodium hydroxide. And because sodium hydroxide is a strong base, its conjugate's not going to have an impact. But for this problem, I'm okay with just telling you, sodium doesn't have an impact on the pH. So now, for the initial pH, this is problem 1. Because we're a buffer, and we're going to assume in this case that we can assume x is small, we can use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the concentration over the base divided by the concentration of the acid. So we know the base and acid concentration already, but we need to know the pKa. So as a reminder, pKa equals the negative log of your Ka. With a quick refresher that anything, that p term just means negative log. So pH is negative log of H plus, pOH negative log of OH minus. So in this case, pKa, negative log of Ka. So if we do that, I lost my pointer, we put that in, we will get that the pKa is, let me put that in my calculator, negative log 1.8 to the negative fourth. We're going to get 3.74 as our pKa. Then we need to plug it into our equation. pH equals 3.74 plus the log of the concentration of our base. Remember, that's going to be from our sodium formate. That's going to be 0.150 molar. And our acid is going to be 0.200 molar. So if we plug all those numbers in, we'll get a pH of 3.615. Note, I'm keeping one more decimal here than we usually do because it's going to help in the second part of the problem. For the labs you're working on, I'm perfectly fine of reporting it to 2 decimal places. I'm just keeping this one to show there is a change because the change is so small you don't see it if you don't go out to an extra decimal. So the second question will take a bit more work. It asks us if we stress this by adding so much sodium hydroxide, what will be the new pH? So first, I'm going to clear this stuff off. And now we'll look at that. So to do this, part 1, we have to identify what reaction is going to take place. So we're adding NaOH. NaOH turns into Na plus and OH minus. So again, this OH minus is the part that's actually going to take part in our reaction. The sodium's just going to float around. And so this will be a base. And if you're adding a base to your buffer, that means it's going to react with the acid. If you were instead adding an acid like HCl, which you also do in the lab write-up, it would react with the base portion. So you have to write a new reaction where you focus on what part's actually reacting. So here, we have formic acid, HCOOH, plus our hydroxide, OH minus. It's going to react, and note both of these are aqueous. To form, we'll form some HCOO minus aqueous, and then since the hydroxide's gaining a proton from formic acid, it's just going to form water. Now to do this, we're going to use something called a BAA table. It's similar to an ice table, but it's organized differently because it looks at the number of moles present rather than the molarity, and it's not based on an equilibrium constant. So to do these, we have to start by finding out how many moles we have of each of these compounds. So I'm going to do this up here. So we're going to start with, I want to know the moles of my formic acid. So to do that, we need to take the fact that we started with 0.250 liters, that's just converting milliliters to liter by dividing by 1,000. We need to convert it into moles. So a reminder, anytime you see this molarity symbol, it's a way of saying like 0.200 moles per 1 liter, which you could also write as 1 liter on top and moles on bottom. But in this case, because the liter is in the numerator here and in the denominator here, so every 1 liter of this solution, I have 0.200 moles of my formic acid. So this one, we just have to solve out like this, and we get 0.0500 moles. Now I also want to know the moles of my formate ion, HCOO-. So for that one, again, we start with 0.250 liters because it's in the same container. If it had been a different starting container and we mixed them together, we would calculate the moles with the volume of that container instead. But these both start out mixed together. So there's 1 liter in here for every 0.150 moles of NaHCOO. Then we can check and we can see that every time you have a mole of sodium formate, it's going to break apart into 1 sodium ion and 1 formate ion. So it's just a 1-to-1 ratio here. So each time you dissolve one, it's also going to give you a mole of our formate ion. Note that you could have a setup where you ended up with 2 ions because it was something like calcium formate where you'd have CaHCOO2. So you'd have to worry about the fact that each mole you dissolve made 2 of them. So you just have to pay attention to that part of what's actually dissolving. So here you go to do this math and you'll get 0.0375 moles of your formate. So now we put it into what we call our BAA table. So B stands for before. How many moles do you start with? So we start with 0.05 moles of this. We start with approximately 0 hydroxide. We're not going to worry about any we do have. And we're going to start with 0.0375 moles of our HCOO-. Now, what we're going to add is we're specifically adding sodium hydroxide. So if you use this 4 milliliters of 0.100 molar, and you go through and do that, you'll find that you're adding 0.0004 moles, doing the same type of calculation I did for the first 2. And we're not worried about the water because it's a liquid. We're not going to worry about changing it. So then what you're going to do is you're going to calculate what it's going to be after addition. And the idea behind this is since you added some hydroxide, it's not going to be stable in the same place as a weak acid. So you have an acid and base together, specifically a strong base. The strong base isn't going to stay there. It's going to react with whatever acid's present. So when it reacts, that means we're going to get rid of it. So we're going to lose 0.0004 moles of this as it goes away. We're also going to lose 0.0004 moles of our acid because every time a base molecule reacts, it uses up one of the acid molecules. Now, since the hydroxide takes a hydrogen away from formic acid, it's going to form more HCOO-. So over here, we're going to get plus 0.0004. So we're going to lose some acid and gain some base. This is how a buffer works. So when we add all this up, our final after addition totals, that's where our third column is 0.0496 moles. We have no extra hydroxide here, and we have 0.0379 moles of this. Based on these new values, we can use our Henderson-Hasselbalch equation of pH equals pKa plus the log of the base over the acid. Note, this equation, as written, is written as concentration. We are not going to discuss in great detail, or if you come by to my office, I'm happy to talk to you about why. You can also put moles into this equation instead of molarity. Please note, this is not normally something you can do. It has to do with the fact that the volumes end up canceling out so they don't matter. But this is not something you can universally do. Every time you see a concentration, you can't just put in moles. But specifically in the case of the Henderson-Hasselbalch equation, because the base and the acid are present in the same container to make a buffer work, you're allowed to just put in moles. Only use that exception here. Don't use it on other problems that involve concentration. So pH equals our pKa is 3.74. Plus, we have the log of our base over our acid, which will be 0.0379 divided by the acid, 0.0496. So make sure to pay attention. This is the one over here. This formate ion has one less hydrogen. It's still our base. So if you go through and you plug that in, you'll get that the pH is 3.623. So the reason I added the extra decimal was because the other one was 3.615. Both run to 3.62. This doesn't change the buffer a whole lot. So I just wanted to show that, so I gave it the extra decimal. In terms of working at the lab, the one other thing to remember is this was the base case. So for the acid case, I'm going to erase this slide now so I can show you this. I'm not going to go through and solve the whole acid, but remember, if you add an acid like HCl, that's going to turn into, when you do that, it's a strong acid, so one direction, it'll form H3O plus and Cl minus. And the H3O plus is the part that's the acid part that's going to be relevant. So the acid is going to react with the base, not the acid in our buffer. So our reactant in this case is actually the HCOO minus ion plus H3O plus. Those are going to react to form more formic acid and some water. So the important part about this is when you add an acid, it's going to make new weak acid molecules and take away some of the base molecules. So you have to write a different chemical equation for it. This should get you through the first few of the buffer. For the last couple problems in the lab, we have some where you just have a strong acid and you're adding water. Those you calculate, you have to find how many moles of acid you have and figure out the molarity of it, so you can take the negative log of that to get the pH. It's just like a strong acid problem would be in your lecture, or a strong base problem. There is no buffer in that case because there's no weak acid conjugate base connection to help do that. So Henderson-Hasselbalch isn't relevant for the last couple of problems when you're working through, so this is assuming you're doing this for the lab. So it's not really relevant for those. Those you just do a strong base or a strong acid problem. Hopefully this helps out, and I will see you soon.